Hi, this is Dr. Xu, teaching mine ventilation for mining engineering college students. In this video, we will talk about how to solve a simple ventilation network. There are three procedures to solve a simple ventilation network. The first procedure is to redraw the circuit. For example, if we have a ventilation network looks like this, it is drawn on a two-dimensional space, but it represents a three-dimensional visual effect. What we want to do is to redraw it so the relationships between airways are easy to identify. For example, on the right, we can see that airway 2 and 3, they are in parallel, and airway 5 and 7, they are in series, and together they are in parallel with airway 6. So we want to redraw the ventilation network so it's easier to see the relationships between each airway. The second step is to work forward to calculate the equivalent resistance. Eventually, we want to reduce this ventilation network to one single airway with an equivalent resistance and quantity flowing in the airway. The last step is we work backward to solve the airflow rate in each individual airway. Let's look at an example. In this example, the total flow rate exhausting from this mine is 50 cubic meter per second. The arrows here indicate the flow direction. There are 10 airways numbered 1 to 10, and the resistance of these airways are all given in this table. The question asks us to find the mine total pressure drop. As we know, pressure drop equals to RQ squared. Q is 50, but the R is the mine total resistance we need to calculate. We find the mine total resistance by reducing this mine ventilation network to one single equivalent airway. Let's see how we do it. The first step is to redraw the airway so the relationships between airways are clear. But in this example, the relationships between airways are clear enough, so I don't need to redraw it. As you can see, airway 4, 5, and 6, they are in series, and airway 7, 8, and 9, they are in series as well. We can reduce airway 4, 5, 6 to airway A. We can reduce airway 7, 8, and 9 to one single airway B. Using the equation, we can calculate the resistance of airway A. RA equals to R4 plus R5 plus R6. Equals to 0.08 plus 0.15 plus 0.16 equals to 0.39 Newton second square divided by meter to the eighth. Similarly, the resistance of RB equals to R7 plus R8 plus R9 equals to 0.1 plus 0.17 plus 0.15 equals to 0.42 Newton second square divided by meter to the eighth. Moving one step forward, we can see that airway A and airway 3, they are in parallel. We can reduce these two airways as one single airway C. We can calculate the resistance of airway C. RC equals to parentheses square 1 divided by square root of RA plus 1 divided by square root of R3 equals to 1 divided by square root of RA. We just calculated it is 0.39 plus 1 divided by square root of R3, it is 0.1. If you do the calculation, the result is 0.044. Keep moving forward. We can see that airway 2 and airway C, they are in series. I will reduce these two airways to airway D. The resistance of airway D, RD, equals to R2 plus RC equals to 0.15 plus 0.044 equals to 0.194. Moving forward to further reduce the airways, we can see that airway D and airway B, they are in parallel. We can reduce them to airway E. By using the equivalent resistance calculation method for airways in parallel, we can calculate the resistance of E equals to parentheses square 1 divided by square root of RD plus 1 divided by square root of RB equals to parentheses square 1 divided by square root of RD. We just calculated it. It is 0.194 plus 1 divided by square root of RB, which we have calculated before. It is 0.42. Finally, it equals to 0.069. Finally, we can see that airway 1, E, and 10, they are in series. We can reduce these three airways into a single airway F. The resistance of F, RF, equals to R1 plus RE plus R10 equals to 0.05 plus 0.069, which is the resistance for airway E we just calculated, plus 0.04, which is R10. 0.05 is R1, which is also given from the table. Finally, RF equals to 0.159. Now we have reduced our complicated ventilation network to a single airway F with equivalent resistance of 0.159. And the quantity flowing in it is 50 cubic meter per second. Therefore, we can calculate the pressure drop P equals to RQ square equals to 0.159 by 50 square equals to 397.5 Pascal. So moving forward, we have calculated the mine total resistance by reducing the mine ventilation network to a single equivalent airway. And we have calculated the total pressure drop in the mine by using P equal to RQ square, and R is the total resistance of the mine, which is the equivalent resistance of the final one single airway, and R is the total resistance of the mine, and Q is the total airflow in the mine. The next question is to find the quantity of air through each airway in the ventilation network. We will work backward to solve this problem. From the last step in the previous slide, we have this one single equivalent airway F. It came from three airways, airway 1, E, and 10. The quantity in this single airway is 50 cubic meter per second. Because airway 1, E, and 10, they are in series, the quantity flowing through them should be all the same and equals to the quantity flowing in the equivalent airway. So they are all 50. So Q1 equals to QE equals to Q10 equals to 50 cubic meter per second. Keep moving one step back. Airway E came from the two parallel airway D and B. The total airflow to airway D and B is the quantity flowing in airway E, that is 50 cubic meter per second. We will need to use the quantity divider rule. QB equals to QE square root RE divided by RB equals to 50 by square root 0.069 divided by 0.42. Finally equals to 20.27 cubic meter per second. QD can be calculated in the same way. Equals to QE square root RE divided by RD equals to, if we plug in the numbers, we get 29.73 cubic meter per second. or you can use Kirchhoff's first law. If we look at this node, Q1 flow into the node, minus QD minus QB equals to 0. Because the flows in airway D and B are leaving from the node. Q1 is 50 minus QD minus QB, which is 20.27, equals to 0. We solve QD, we can get the same value. Moving backward one more step, airway D came from airway 2 and airway C in series. As airway 2 and C are in series, the airflow quantity in them equals to that in airway D. So Q2 equals to QC equals to QD equals to 29.37 cubic meter per second. Moving backward one more time, we can see that airway C came from airway A and airway 3. Airway A and airway 3, they are in parallel. Therefore, the air quantity flowing in them can be solved by using the quantity divider rule. QA equals to QC. QC is here. That's the total air quantity flowing into airway A and airway 3. So QC by square root RC divided by RA equals to 29.73 by square root of RC 0.044 divided by 0.39 equals to 9.99 cubic meter per second. By using Kirchhoff's first law, Q3 equals to Q2 minus QA equals to 29.73 minus 9.99 equals to 19.74 cubic meter per second. Now move backward one more step. Airway A came from airway 4, 5, 6 in series. Airway B came from airway 7, 8, and 9 in series. We know that for series airways, the air quantity flowing in them is the same as air quantity in the equivalent airway. So Q4 equals to Q5 equals to Q6 equals to QA equals to 9.99 cubic meter per second. Similarly, Q7 equals to Q8 equals to Q9 equals to QB equals to 20.27 cubic meter per second. So now this ventilation network is completely solved. We know the air quantity flowing in each airway. We know the resistance of each airway. We can calculate the pressure drop in the entire mine, and we can also calculate the pressure drop in each individual airway, because we know the resistance of that airway and we know the airflow quantity in the airway. And pressure drop equals to RQ square. For example, if I ask what's the pressure drop in airway 8, P8 equals to R8 by Q8 square. R8 is given and Q8 is calculated here. By using the calculated numbers, we can calculate the pressure drop in airway 8. Here is an example for you to practice. In the following ventilation circuit, the mine quantity is 60 cubic meter per second. Calculate the total equivalent resistance and calculate the quantity and pressure drop in each airway and fill in the table. So 60 cubic meter per second of air come out from the mine, and the airway resistances are given. Here, as you notice, airways C, D, and E, they have the same resistance, and they are in parallel. We can calculate the equivalent resistance of the three airways by using the equation Req equals to parentheses square 1 divided by square root of R1 plus 1 divided by square root of R2 plus you may have more than 3 airways, and finally plus 1 divided by square root of Rn. If R1 equals to R2 equals to all the way to Rn, and let's say it equals to R, and then the equation becomes Req equals to parentheses square 1 divided by square root of R plus 1 divided by square root of R plus all the way to the last one, 1 divided by square root of R. We can simplify this expression. It becomes R divided by N squared. R is the resistance of the airway. Because the airways are all the same, they all have the same resistance R. And N is the number of airways in parallel. So if there are several airways in parallel and the resistances of these airways are the same, we can use this simplified equation. Of course, you can use this original equation to do the calculation and you will get the same result. Okay, I ask you to pause the video and take 3 minutes to solve this problem before you continue watching the solution. Alright, pause the video now and you have 3 minutes. Okay, I believe you have tried to work out this problem, and here I will show the result to you, and you can compare your result to the correct answer. Hopefully you have solved this problem correctly. Finally, we have talked about how to solve a simple ventilation network. But what is a complex ventilation network? Look at this example. You have a fan here, and the airways are connected like this, and there's no way you can reduce these airways to a single equivalent airway. So we are not able to reduce the network to a single equivalent airway. This is because we don't know these two airways, are they in series or parallel? It's not clear. The same with these two airways. And we cannot apply the equations for airways in series and parallel to reduce them. However, we can still solve them by using a different method. It is called the Hardy-Cross method. It is an iterative method that is commonly used by ventilation network analysis software. And this is not the scope of this video. Alright, in this video we have went through the procedures to solve a simple ventilation network. So there are 3 steps we need to follow. The first one is to redraw the circuit so the relationships between the airways are easier to identify. The second step is to work forward to calculate the equivalent resistance of the entire mine and thus calculate the total pressure drop of the mine. And finally, we can work backward to calculate the quantity in each of the airway. Please leave a comment if you have any questions. Thank you very much for watching. If you feel this video is helpful, please subscribe, like, and share. This is Dr. Xu. I will see you in the next video.